as you can see, I'm going to present a paper called Breaking the Barrier of Hard Samples. So this is a data-centric approach to synthetic data for medical tasks. So I will first introduce the backgrounds of the problem setting. First, real world data sets in the medical domain are very small and noisy, and there are a lot of privacy issues with it, and also due to the diverse of different patients, so having an unbiased data set is often very hard than usual tasks. So as a consequence, so models trained on this a lot of limited data sets are often biased and fail to generalize across diverse patient populations. As many researchers often work on the fairness algorithms or architectures that targeting these issues. But this paper provides a view from the dataset itself. So this paper mainly provides an approach that targeting those issues in existing data sets. So let me first introduce what are hard samples. So the hard samples usually refers to those data points that models don't usually learn from a reliability way. So some causes the model very confident, but actually it predicts wrong. And some also causes models with low confidence, but usually it gets a great result. So also there are some data causing models to less on the decision boundaries. So these data are usually very detrimental to the model's overall performance. As a solution, so this paper introduced a systematic framework designed to enhance the generation and refinement of synthetic data by incorporating a profiling technique. So this is kind of a filtering, but with higher qualities. So the goal of this paper is to ensure the hard-to-learn samples are considered from the generation process to the synthetic samples. So in summary, this paper has four main contributions. So this framework helps to reduce the predictive errors in its experiment. So it's in this paper they applied it in regression tasks, and also this paper helps models to perform more stably by its performance. And also there are also two interesting points. So the third is that the synthetic data generated through this profile to generation data pipeline sometimes performs even better than the real world data. And lastly is due to it is a synthetic data technique, so it helps to maintain the minority group proportions. So it avoids the bias caused by inside the data from real world. And now I will introduce the profile to generation workflow. So if anyone needs more clarify on the background. Okay, I will continue. So uh, so we start with the original real world data sets, and we apply a profiling framework. So in this paper, they use Clean Lab or Data IQ. So Clean Lab is designed mainly for classification tasks. So it looks at the prediction probabilities and can tell if a sample is easy, hard, or possibly mislabeled. And Data IQ Reg is extension of this idea to the regression tasks. So instead of classify the probabilities, it use a matrix like residual errors and prediction variance to measure whether a point is easy, hard, or ambiguous. So the choice of the classifier framework is really depends on what task you want to perform. So whether it's a regression task or it's a simple classification task. Um, so now what we do is that we randomly how we decide like which profiling method actually work better. So what we do is we randomly flip some data points. So and we let all the data to pass through the data profiling framework. So we use the F1 score to measures how this works. In the next page, I will explain how the criteria work. So we have three matrices. So the first is recall. So recall asks, so basically out of all the flipped labels, which are our ground truth and hard samples. So how many did we actually catch? So out of all the actual flip labels, because we know how many we flip, right? And after the profiling, we can also count how many those flipped ones were catched. And also we also have the precision, which asks out of all the samples we marked as hard, so how many were truly flipped? So combining these two, the F1 score balance them. So we don't only focus on catching all everything, but also we don't want to be overly strict. So this is kind of a balance spot. So in profile to generation framework, the profiling method is the one which method that achieves the highest F1 scores. And if two methods are like they achieve equal F1 score, then in the paper the author just randomly pick one method. In step two, we generate the synthetic data. So I think this is the key idea in this paper. So instead of training one big generative models on the entire data set, they train separate models for each subgroup they marked. So later on, I will show how many their classified subgroups. So that means that one generator is for easy samples, one for hard samples, and one for those lies on the decision boundaries. And the reason this separatism is to prevent a phenomenon, what they called is distribution pollution. So it basically means that if you mix everything together, then the generator might overfit too easy samples and ignore the harder case. So splitting is a good idea to learn that easy distribution and those hard samples distributions. So yeah, so in the end, they specify it to three subgroups, which is easy, hard, and ambiguous. And lastly, they also do a stage called refinement. So if they set a threshold, so they are keep removing those hard samples. So by the hard samples, as I just mentioned the definition, so those hard samples are causing models hard to learn. Like uh, as I mentioned, is some that actually wrong, but models be confidently correct on that, and some are actually correct, but models are not that confident for their correctness. So this is a graph for their procedure. So as we can see, this is a huge collection of data points, and they use profiling to separate each part of the data according to their hardness regarding to the model's learning. And they train separate generative models to generate the synthetic data. So these are from real data, and these are from the synthetic data the generative model just generate. And they also mix these synthetic data, and also they do it again and again. So maybe quite few iterations to repeat this procedure. And also, as I mentioned, the framework, the profiling method, which is I mentioned here as the framework. So whether which framework we use to profile those data are very important. So so the way we use is just the paper mentioned is just the F1 score I just mentioned, and they want to keep those framework which has the highest F1 score. And also this is a threshold. As we can see, we drop the hard samples as I mentioned here. So this is a threshold on how many hard, how many those samples we want to drop. So it is in the paper they did not treat it as a hyperparameter. So they optimize it jointly with the framework. So you can imagine that there is a list of frameworks and there is also a list of thresholds. So it's a combination of each pair, and they see which one achieves the best performance F1 score. So I think it is clear that a higher threshold will drop more hard samples. So as I mentioned earlier, so it is always better to find a sweet spot. So it's not neither too hard or too easy for them. Uh, am I clear? Oh, okay. I think I can continue to the experiment. So I'll mention the general setup uh, in this paper. So they compared two baseline methods. So one is the traditional one. So no profiling is used. And the other is the pre-processed one. So they profile, so they do the filter, but they didn't do the refinement. So they didn't, although they do the profiling, but they didn't drop the hard samples. And the data set they use is the public data sets from the open machine learning. And so also they use generative models to generate the synthetic data. So is that they first use real world data to train the generative models and then use the generative models to generate the data. And also they also introduce the evaluation models. So for their tasks, these are the regression models. So they measures the effectiveness of the quality of data through the accuracy of these regression models predictions. So their evaluation protocol is training on the synthetic data they generate, but test them on another part of the real data. So so I want to mention here is the matrix, since it is a regression prediction. So they just use the root mean squared error. So it measures the prediction and it measures the distance between the prediction and the real position. So it is the smaller the mean square error is, so the better the predictive performance is. No, I will go through the results. First, since it is a synthetic data generation task, we're always interested in how similar this synthetic data is compared with our real samples. So they use a Washington distance to measure the efforts of to measure such similarities. So Washington distance is a measure that measures you can imagine it measures the effort of transporting one distribution into another. So this method is basically compare how close two groups of data points is. And I when I was reading this paper, I think one question that I was asked is that why not they just use a KL divergence to measure such a distance? And it turns out that one drawback for KL divergence in this situation is that if there is no overlap between the two groups of data, then the KL divergence will go to the infinity. So is KL divergence is randomly sample Px over Qx, and if Px is not zero, but Qx is zero because there is no overlap, so then it goes to infinity. So I think that's the main reason why they use the Worthington distance here. And also the I will also introduce their results by two graphs. So one is the bar graph, and the other is the welding laws. So they are all in next page. So we will go it very soon. And I will mention the conclusion first. So the conclusion, they show that the profile to generate synthetic data which is closer to the real world data. And this is a violin plot. So actually, this is my first time of seeing this plot. So on the very left side is the real data distribution, and these are all the synthetic generated. So the more close the shape looks to the real, the more similar the data being closer to real. I think that's a very big picture of this plot. And we can see that through the profile 2G, so this is quite similar. And also this is, oh, this is not that similar. So they just compares it, the similarity through this way. And also, we also consider the similarity between the synthetic data and real samples through a bar graph. So we can see that through this example, it measures the the distance between those synthetic data and the real world data. So it compares the traditional way, which is just directly using a generative model to generate, and the pre-processed way, which is generate, but which is with profiling but without refinement, and their best way, which is profile to generation. So which is generate a profile and iterative refinement. So we can see that this one is quite low, right? So the most blue one. So this one, it means that the Worthington distance for the synthetic data that's generated by the profile 2Gen is quite it is the smallest distance from the real data. And also it also shows as I just mentioned, they use the how good the trained regression models on this data to measure the effectiveness of this data. And we can see that through this graph, I think it is clear that traditional way has the highest mean square error. And once we add profiling, it gets a lower mean square error. And once we also add the refinement, which is their ultimate profile to gene framework, it achieves the lowest mean square error. So yeah, this is good because we want our the models that trained on the synthetic data has better prediction accuracy. Also, they also work on the data augmentation tasks, and this is the result. So the result is that the lower the mean square error is, so the better their data augmentation efforts is. So we can see that they achieved, I think most of them, they achieved good results. So they lower the mean square error, which is also good. And also, we can see that since they have a refinement step, which is drop those harder samples. So they actually have less samples than the original data. But they trained it on this two group of data. And in some case, maybe I will show this case. So this is still the y-axis is still the mean square error. And you can see that even though they use less data, but they sometimes still achieve better performance, which means that the synthetic data can not only be similar to the real data, but also sometimes be more effective in the augmentation tasks to help train the models. However, this is some drawbacks. So this plot is different. This is 4 runs with four different Cs. And we can say that sometimes the models often have the high variabilities, so it's not performance that stable. So this is one drawback of their this method. So it really depends on the Cs and depends on the different runs. So it's not always that stable. Yeah, so I will conclude the limitations. So the performance, as we can expect, of this method is usually varies by the data sets and the models a lot. So it's not a one-size-fits-all solution. And some models has higher variabilities across different Cs and different runs. And also for some data sets, it is better that not dropping those hard samples rather than dropping those hard samples. So profile tuning is not always the optimal solution. And also, as we can expect, so synthetic data is can never like fully replace the real data completely in the medical domain. So I will have few points for the conclusion. So the first point is that by dropping those samples that models feel struggle to learn, it can actually improve the regression performance. And also, it is always better to provide better, higher quality synthetic data sets rather than like a lot of data sets with lower quality, because sometimes the smaller high quality data set helps to achieve equal or even higher performance. And the key takeaway of this paper from its authors is that focusing on hard samples profiling leads to a stronger and more reliable synthetic data generation. And in my personal view, I think it could be an approach in having, especially in tasks, like if we want to have, for example, a data augmentation task, is always better to at the filtering stage and keep those high quality data points. And yeah, so I think that's all of my presentation. And if you have any questions, so we can discuss.